Hello, this is Lisa Knight. This lecture will discuss electromagnetic waves and their properties. Electromagnetic fields are produced by oscillating charges. Imagine that we had a charge oscillating up and down, as illustrated in figures A, B, C, D, E, and F. The change in electric flux as it oscillates up and down will produce a magnetic field that is perpendicular to the electric field. The electric field produced by, say, an antenna connected to an AC generator propagates this way, away from the antenna, analogous to a wave on a string moving away from your hand as you wiggle it up and down. The result is what we call an electromagnetic wave. Notice that the electric field is vibrating up and down, and the magnetic field is forming perpendicular to that, vibrating left and right. The direction of propagation and the directions of the electric and magnetic fields in an electromagnetic wave can be determined using the right-hand rule. If you point your fingers of your right hand in the direction of E and curl your fingers towards B, your thumb points in the direction of propagation. Anytime an electric charge is accelerated, it will radiate. Accelerated charges radiate electromagnetic waves. All electromagnetic waves propagate through a vacuum. They do not have to have a medium to propagate. And their speed in the vacuum is 3.00 times 10 to the 8th meters per second. However, when the light, for example, moves into air or water, it will slow down significantly, but it will never go faster than the speed of light, c. The speed is so large that it's very hard to measure. The first measurements were done in the late 1600s using the eclipses of moons on Jupiter. In the 19th century, a ray of light passing through a notched mirror was able to derive the speed of light from the rotational speed of the mirror and the distance from the wheel to the mirror. Also, the value of the speed of light is related to the electric and magnetic fields. If you remember, we learned about the permittivity of free space, epsilon naught, and the permeability of free space, mu naught, when we talked about electromagnetic waves. It turns out that the speed of light is equal to 1 over the square root of epsilon naught times mu naught. This is a very, very large speed on an astronomical scale. It can take light a long time to travel from one star to another. Astronomical distances are often measured in light years. A light year is not a unit of time. It is the distance light travels in 1 year. Light from the Andromeda galaxy left takes about 2 million years to reach us from the most distant galaxies in the Hubble Deep Field image right. It takes 13 billion years to reach us. So ponder that when you look up at the night sky. You're actually looking back into time, millions and millions of years, and seeing the sky as it was then, not as it is now. The Doppler effect also applies to electromagnetic waves. The speed of the wave in the vacuum does not change, but as the observer or the source moves, the frequency does. So if a star is moving away from us, the light appears to have a longer wavelength, whereas redshifted. If it's moving towards us, the light appears to have a shorter wavelength, and it is blue shifted. Because all electromagnetic waves have the same speed in a vacuum, the relationship between wavelength and frequency is simple. Remember that V equals lambda F. So C equals lambda F. The full range of frequencies of the electromagnetic waves is called the electromagnetic spectrum. The longest wavelength of the spectrum are radio and TV waves. Next, shortest are microwaves. Infrared waves are just a little bit too long for us to see. Then we have a very small portion of the spectrum that's the visible light that we detect with our eyes. Light that's just a little bit shorter wavelength than we can see is ultraviolet. And then next to the shortest wavelengths are X-rays, and the shortest wavelengths are gamma rays. Notice that the shorter the wavelength, the higher the frequency, and the more damaging the rays are. Gamma rays are a form of radiation. X-rays are too. And so is ultraviolet. So all of those are not very healthy for us because they're high energy waves. Radio waves are the lowest frequency and range from 10 to the 6th to 10 to the 9th hertz. Microwaves are used for cooking and are also for telecommunications. Microwave frequencies are from 10 to the 9th hertz to 10 to the 12th hertz, with wavelengths from 0.3 millimeters to 30 centimeters. It's important to note here that the frequency of an electromagnetic waves defines what it is. Radio waves always have frequencies between 10 to the 6th and 10 to the 9th. Microwave has frequencies 10 to the 9th and 10 to the 12th. Infrared waves have frequencies 10 to the 12th and 10 to the 14th hertz. This is what we use to sense heat, and remote controls use them as well. Visible light has a very, very small frequency range, 4.3 red light times 10 to the 14 hertz to 7.5 10 to the 14 hertz violet. Ultraviolet starts with frequencies as low as 7.5 10 to the 14th to 10 to the 17th hertz. These rays cause tanning, burning, and skin cancer. Some insects can see ultraviolet, like pollinators. X-rays have even higher frequencies, 10 to the 17th and 10 to the 20 hertz, and they're used for medical imaging. Gamma rays have the highest frequencies of all, 10 to the 20 hertz and above. These rays are extremely energetic and are produced in nuclear reactions, and they are extremely destructive to living cells. Also, electromagnetic waves can be polarized. In other words, they can be forced to vibrate in just one or two ranges of direction. To do that, you put a polarizing film in front of them, like polarizing sunglasses. The polarizing film only lets one direction of light propagate through. So it may only let vertical oscillating light through. So if you try to send just general white light that's vibrating in all directions, only light that's vibrating in the vertical direction will get through. You can also, so polarizers allow it to pass through in one direction. So if you pass it through one filter that allows up and down vibrating light through, and then you put another filter in front of that that's oriented sideways, it'll completely block out the light.